Joining. I think we can start. Welcome to this week Autonomy Talks. This week is a great pleasure to have Professor Kyriakos Vamvoudakis, who is currently an assistant professor in the Daniel Guggenheim School of Aerospace Engineering at the Georgia Institute of Technology. So something about Kyriakos: he was born in Greece and he received a diploma in electronic and computer engineering from the Technical University of Crete in Greece. And he then moved to United States, where he was in many places. So he first studied at the University of Texas, where he received his Master of Science and his PhD in electrical engineering. He then worked for a while as an adjunct professor at the University of Texas at Arlington, before moving to California, where from 2012 to 2016, he was a project scientist at the Center for Control, Dynamical System and Computation at the University of California, Santa Barbara. He then started as an assistant professor at Virginia Tech, where he stayed until 2018 before joining Georgia Tech. His research interests include reinforcement learning, control theory, cyber physical security, bounded rationality, and safe-assured autonomy. And today he's going to talk about bounded rationality methods in reinforcement learning driven autonomy. We are all very interested in learning more about this topic, and that's why I let the stage to you. Kyriakos, go ahead.
Thank you very much, Joel. Thank you very much for this kind introduction. Thank you for the invitation. It's a pleasure being here and to see old friends, and as I say, also make new friends. So, so you can interrupt me anytime you want. I'll be happy to have an interactive talk, so don't hesitate to interact with me while I give my talk. So today's talk is on bounded rationality methods in reinforcement learning-driven autonomy, and I will explain what I mean by bounded rationality pretty soon. So hopefully you can see my my presentation. Okay, so this is the outline. Okay, so I will motivate the work, why we want as control theorists and as people working in autonomy to work on something which I will explain, and we call as bounded rationality, where everything is not happening at the equilibrium, especially for games, but also in a different levels of intelligence. So I will describe different frameworks that they can incorporate bounded rationality. So I will start with an easy case of linear quadratic games. Then I will go to nonlinear systems and specifically to pursuit evasion games. Then I will show how this also can be applied to stochastic games. And then finally, I will talk about what we call Metalearning, where we want to see how bounded rationality can be used to learn other agents' learning mechanisms and infer them. And then finally, I will conclude the talk about future work. Okay, so the motivation why we want to work on such a topic. So, so our main area of application is any kind of cyber physical systems. So where they have a physical and digital layer, and several applications can be seen here. So from healthcare, aerospace, and so on and so forth. And of course, one very important thing is security. So cyber physical security is different from classical cybersecurity because it considers also worst case attacks and attacks on the physical component of the agents. So we want to find, and also humans are part of cyber physical systems. So if the attackers, which most of the cases are humans, so we want to understand how they behave and predict their capabilities and policies, and based on that derive our mitigation strategies. And also, in order to do that, we also want to understand if and how they can use learning mechanisms to attack us. So you will see what I mean by it pretty soon. And then, of course, several news have been on that. Okay, so now let's actually say why we want to work on this bounded rationality, because as I said, I want to predict human behaviors. And I want to predict human behaviors, especially for human AI autonomy and security concerns. Okay, so as control people, I think if we combine optimization methods with game theory, we can eventually have different kinds of equilibrium, which, of course, the one famous is Nash. Of course, other equilibria can arise, like Stackelberg, and so on and so forth. But of course, all these equilibria, they assume perfect rationality, and this makes it for predictability. And also sometimes computing Nash equilibria or Stackelberg equilibria is computationally infeasible. So also, but in multi-agent scenarios, we want to see what is the objective of the other agents, what is the intelligence of the other agents, and if they're cooperative or adversarial. So bounded rationality will help us answer these three questions. Okay, so I already said most of these things, but I want you to see one important thing of bounded rationality. So people in behavior psychology have been using two kinds of bounded rationality. So one of them is called level K thinking, and the other one is called cognitive errors. Okay, so you can think that you have different agents where all the agents, they have different levels of intelligence. Okay, so for example, they have different computational capabilities, different learning mechanisms, different, I don't know, attacking perspectives, they're insider threats, or different, or they change teams even during learning. So, and then behavior psychologists actually have shown that if you play the Nash equilibrium, then you're up to level 3 intelligent. Okay, actually, most humans are up to level 3 intelligence, but Nash equilibrium is level infinity. So, I also want to point out this this thing. Okay, so now let's talk about level K thinking cognitive hierarchy. So, every time I talk about level 0 agents, so these are the non-strategic agents. So you can think about random players. Mostly, they don't know that other agents exist, or they're just random things that they just play random strategies. Level 1 players, they actually optimally respond to level 0, and level K, and we go recursively up to level K, where they optimally respond to level K minus 1. So cognitive hierarchy on the other side, they don't assume that we have only one step, but that the previous level K thinkings are based on different distributions. You'll see what I mean. Okay, so now let's actually start talking and putting some math there. So since we're control people, we love to start everything easy. So we will start with a linear system where x dot equals kx plus b u plus kd, where I want to design my controller u, and b you can think is an adversary with different kinds of intelligence. Okay, so if I can go back to zero-sum games, I'm sure that we're all familiar with minimax optimization frameworks, where here you see I want to minimize u and I want to maximize the disturbance. Okay, so this actually goes back to the roots of H infinity control and so on and so forth. Okay, so of course, if you do the rationality conditions, you can actually find the optimal u and the optimal t. This is kind of straightforward. And then if you put those back to your Hamiltonian, then you'll find the famous Hamilton-Jacobi-Isaacs equation. But of course, all these things, they assume perfect rationality, and they eventually converge to the Nash equilibrium. Okay, but we will take it one step further, and we will not assume about infinite rationality like what happens in a Nash equilibrium. Okay, so let's say how we can do that. So wherever now I talk about bounded rationality, it's something like imperfect learning, or for those of you who work on learning, you can call it like truncated policy iteration. Okay, so you can think now that I have a defender, which is my u. Okay, so if it is of level 0, which is the anchor policy, I don't know the existence of a disturbance or an adversary. Okay, so I will naively solve this Riccati, take my controller, and then substitute it. Okay, and then the attacker also solves a naive game by assuming that my control is also Q0. Okay, and then I take it one step further, and then for level 1, I will assume that, and of course, this is the Riccati equation that eventually has to be solved. But again, the level 0 policies, which are also called anchor policies, you can think that they're very naive because either they're random or they don't know the existence of other players. Okay, so if I go up to the next levels, okay, so you will see that my defender strategy has a k. This k doesn't mean iteration, but means the next or the kth level of thinking. So I can derive my level k defender recutting, and then you see I have PD, which is in the previous level of thinking, and PU at the current level of thinking. Okay, because remember, as a defender, I want to derive a framework such that I assume that everybody else is one level below me. Okay, so and then the attacker on the other side derives this attacker strategy, okay, and then solves the level k attacker recutting. Okay, so if you solve these two recutting equations, then eventually we will solve the level k thinking of recutting. Okay, so now, of course, I don't want to do that offline. And if you see the previous recuttings, I also require information about AB, which is not proper for learning. And also, I don't want to do it offline as you solve the recuttings, and I want to do everything online. So what I want to do is I want to derive everything in a model-free fashion. And the first model-free thing that comes to my mind will be Q-learning, which actually was derived by Watkins, but Watkins derived this for MDPs. So what we will do here is we will apply to continuous state and continuous actions. Okay, so you will see that for every level k, we will derive a Q function, okay? And then this is, you can think this is an augmenting state vector where contains the state and the actions. And here's the learn matrix, okay? And eventually, if I learn this matrix, then I have solved the problem. Okay, so the first thing that I want to do is to use a critic actor structure where the actor solves and finds, or if you want to say approximate, the optimal solution, the optimal control input or the optimal defender input, while the critic actually approximates the cost. Okay, so what we will do to actually tune these unknown variables and find them in real time is to use temporal difference errors, okay, which will be specific for every level k, okay? So every level will have an error, and then if we take this to 0 by picking the appropriate weights, I will eventually learn the optimal policy that I have to pick for every level. Okay, so also you will see that this T, so this is how fast I measure my cost, okay? So I interact with agents and then I measure my cost every T IRL seconds. Okay, so eventually, if I want to find, as I said, these W's, if I find these W's, I have solved my problem, and no pre-training is required. So everything will happen in real time by learning the trajectories. Okay, so every level will plug and play this critic actor update loss, and then we will learn the policy and the cost of every level. Okay, but of course, now that I learned the cost and the policies for every level, I want to estimate what are my other agents levels, especially if they are adversarial. So how I will do that? Okay, so the defender will interact with different levels of with different cognitive levels for a predefined time period, which is different than the previous T that you saw, which is the T that I measure my cost. This T in that you see there is how I interact with the other adversaries. Okay. Okay. So what I will do is I will have a database of different policies. Okay, and I will compare these databases with what I see from the other agents. Okay, and after I compare those, I will map those to different levels. Okay, so people in level K thinking or cognitive hierarchy, they use this softmax function that it finds similar behaviors. Okay, and after that, we'll be able to map every policy from the database to a specific level. Okay, so this actually goes back to learning Poisson parameters, because as you saw before, actually I have it here. Okay, so I update my Poisson model like this, and then if I learn the Poisson parameters, eventually I have found what are my other agents. Okay, and this is the distribution of different beliefs about what I believe my attacker levels are. So you see here that I have 5 levels of intelligence, and then I see that every level comes with different probabilities. So of course, I'm not certain about who they are and what they do, but I have a probability that they are of specific levels. Okay, so what we have done is we have done an algorithm framework for level distribution learning, okay? And what I want to do as a defender, I want to determine the intelligence of the attackers in the environment, okay? So as I told you, this thing will let me make a database of learned attack policies and then map these databases back to the level K thinkings. And this, you can see here a little diagram where different kinds of attackers of different levels, they interact with the defender, and then I compare the interactions I see with a database of learned attack policies, and then I map eventually everything to level K thinking and cognitive hierarchy, whatever I use for bounded reasoning. Okay, so now that we started from a simple system, which is a linear system, now we'll go to a harder system where we have end UAVs that are assigned to track an evasive target, okay? So the UAVs in the target will be modeled as Dubin's vehicles. So you see directly that this becomes somehow a harder problem. And the end UAVs that they track this evasive target, they will have also different kinds of intelligence, okay? So again, you can think that you have UAVs, different models, okay? Different computational capabilities and so on and so forth. Okay, so for those of you who like actually kinematics of UAVs, I'm sure you know that you can write them like that, where the xi's are the kinematic models, and then I have everything is moving as a constant air speed, and then the xi3 from you see here is the heading. Okay, so of course, since they're Dubins, I want to bound their tending radius. So as you see here, my UIs are bounded by UIs bar, okay? And then also my evasive target will also have a bounded turning radius. Okay, so of course we can do simple mathematical transformations to transform them to the overall augmented dynamics, which can be given by this system over here. And then eventually I can solve, let me see, yeah. I can define my performance, which performance will be a zero-sum game. First, you can think of an infinite rationality, where the team of UAVs tries to minimize the performance while the target tries to maximize it, okay? And, but I wanted to pay attention that the first component in my performance is actually a relative distance penalty, where this will make sure that at least one UAV will be on top of the target at all times, or see the target at all times, okay? And you can think that these are, this is inspired by resistors, by parallel resistors. Okay, so the further you are, okay, and then you can also tune these beta 1s and beta 2 to check who is closer and who is watching the UAV, okay? Okay, and then as I said, we want our RUU to incorporate somehow, because I don't want to have external constraints, I want to incorporate the input penalty inside the performance, okay? So, because remember that every UAV, even in the target or as a pursuer or as a evader, has a bounded turning radius, okay? So how I will do that is I will incorporate these constraints inside the performance index by using this UAV's input penalty and this target's input penalty, okay? So you can think that these functions are hyperbolic tangents. This theta that you see there, they're hyperbolic tangents, and they penalize and bound the turning radius of the U. Okay, so now, as I said, I don't want to solve this as if everybody had infinite rationality, so I was as a Nash game, but I want to do it as if the UAVs, they have bounded rationality, okay? So in other words, every UAV, every pursuer, okay? You can think you have multiple pursuers, multiple evaders, and all of them, they have different levels, different models, and so forth, okay? So each player in the game will operate under the belief that all her pursuers or evaders, they perform K-1 levels of strategic thinking, okay? So you can think that the level 0 UAV, okay, assumes that the target is not maneuvering, okay? So there's lots of works in the literature where there is pursuit evasion, where the target goes on a straight line, okay? So as you can see here, my cost doesn't incorporate any target for now. Doesn't penalize any target. And then if we go to level 1, okay, so then this UAV will assume that the target is not also evading. So you see here that I have the first level, okay, and then this is my U0, where U0 goes on a straight line, okay. So I derive my policies based that my target is not evading, okay. And then I can generalize that up to level K, where I can have all the every policy that you can imagine. Okay, so again, as you see here, every time I solve the optimization problems, here I have a 0, I have 1, then I have K. But remember that here my evaders are one level below me. Okay, so let's see how this will work. Okay, so so you see with the blue, okay, I have my evader, and then I have two UAVs trying to capture the evader. Okay, so as you see, the UAVs, they're trying to at least one look at the target at all times. And these are just some parameters for the simulation. Again, this assumes infinite rationality, but of course this can work also if you have bounded rationality. And then, yeah, so this is also the relative distance. So you see that they can attain a minimum relative distance of 1.5 meters. Okay, so now let's say that the UAVs and the target, they have bounded cognitive capabilities. Okay, so where one UAV is assigned to pursue a target operating in different kinds of levels. So you can think that they're operating in level 1, level 3, level 5, and level 6. And then they're performing at most, 4 thinking steps. So remember that, as I told you before, in order for me to learn the cognitive capabilities, I have to also learn the Poisson parameters. And then you see that eventually, after a number of interactions, I was able to learn the Poisson parameters. And the spike in the beginning, as you see over here, is that the target performs 1 thinking steps and moves to a higher level of intelligence. And then these are the beliefs over target levels of intelligence. This is what my other agents are doing. And again, so I want you to pay attention that the thinking steps and the cognitive levels, they do not coincide in this way. Okay, so we started from the linear quadratic games. We went to pursuit evasion games with different levels of intelligence. Now we will see how this framework can be applied to a stochastic game, where I give you a finite set of agents, which can be N, a finite action space AI, a finite state space S, and then of course I have a reward per state transition and different transition probabilities. Okay, so the player objective will be to learn a policy PI, okay, which maps states to policy, to actions, to maximize the objective. So from now on, you don't see anything different here. Okay, so you see, so whenever I saw the PI and the P minus I, this is the classical framework where you see the policies of myself and all the other agents. Okay, oops. Of course, in order for me to solve this classical stochastic game, I need a model of all the other agents' policies, PI, to solve this problem, right? So, and also computing this Nash equilibrium is mostly computationally feasible and imposes reasonable assumptions. And this is the classical Nash equilibrium in the stochastic games, similar to the one that you saw before, but now it's adapted to the stochastic games framework. Okay, so what we want to do here is we want to use bounded rationality to relax the assumptions of the equilibrium, okay? And then provide non-equilibrium learning play policies. Let's see how we can do that. Of course, This is also inspired by the Camber and Ho, where they developed level K thinking, which I described before. Again, a level 0 for those of you who want a reminder. So a level 0 agent is assumed to follow naive policy. A level 1 agent is more intelligent and best responds to level 0. And level 2, best responds to level 1, and so on and so forth. Okay. And then, of course, this can go up to K infinity. Okay. Again, the same framework with before, but now we will apply it to stochastic games. Okay. So again, we will start from level 0s. Okay, so we will choose a random naive policy P0 that will correspond to 0 steps of reasoning. Okay, again, this is random. Okay, I put a random policy there and then see what happens. Okay, but now as I go up more the levels, okay, so what I will do is I will pick my policies based that all the other ones are one level below me. Okay. And then I will develop a way to learn this level K bounded rational policy. Okay, so classical things in learning, they're value iteration and policy iteration. So we will see how we can adapt value iteration and policy iteration to learn this level K bounded rational policies. Okay, so for the first one, we will call it level recursive learning. Okay, so we will do value iteration recursively at its level K. And the best and worst case complexity scales linearly to K, which is the level. And then, of course, we have guaranteed convergence. And then we will propose a level parallel learning where we perform value iteration simultaneously at its level K. And the best case complexity is independent of the level K. And of course, here we have to pay a price because the guaranteed convergence is only given uniqueness of its policy, of its level K policy. Again, in order to solve this stochastic game and learn this bounded rational policy, we will provide two different kinds of learning frameworks. One that is more recursive, and the other that is parallel. So here are the two different frameworks. So as you see here, for the first one on the left, you see that each level is learned separately, and the next one is each level learned concurrently. Again, you can think that I have adapted the policy iteration or the value iteration, if you can say. I have adapted the classical value iteration and policy iteration to different levels, okay? And of course, we also provide convergence of everything. Okay, so now we talked about levels K. Okay, so in the stochastic games, we can also apply cognitive hierarchy, where we don't assume that the level K assumes that it's one below, but the level K assumes that all the other agents, they follow a distribution that lies from 0 to K minus 1. Okay, so if I'm player K, so everybody else is from level 0 to level K minus 1. Okay, so now again, the level 0, we have again the random policy, okay? And the level K, I want you to pay attention now that I have this P bar where K follows from a distribution from the 0 to K minus 1, okay? So again, the policies of the other players are not one step below, but they can, they're distributed from in all below levels, okay? Okay, so now let's see how this can work. So let's say that I have two agents in a grid world, okay? They attempt to move vertically or horizontally, and they receive a reward if there is a treasure, where you can see this little box here, and then they receive a penalty if they collide, okay? So you can see, you can think about it as a preservation game, but you have a goal. Okay, so here on the left, you see they repeat until loop iteration number. So I want you to see that this is a comparison of a level K thinking in cognitive hierarchy in the recursive and parallel structure. So again, as you can expect, the parallel is faster, but of course, we have to pay a price for the convergence. Okay, so, and then of course, this is just evolution of one level, okay, level 4, I think, yeah. Okay, and then here also, you can see we have run this framework for 100 different games. where player 2 is level 4, and the level of P1 on the left varies from 0 to 3. Okay, so you see what happens. Okay, so you see that eventually we'll be able to learn the policies. Okay, and then on the right, also you can see this on the cognitive hierarchy framework. So the left is level K thinking, on the right is cognitive hierarchy. Again, similar results. Okay, so now we will talk about how we can apply these ideas to more meta learning. In other words, I want to learn how other people are learning. Okay, so this is another form of bounded rationality. Okay, so you can think that this has connections to quantum responses, fictitious play, and so on and so forth. Okay, so why I want to do that is because the players in a game, they want to change their policies during play. Okay, and we want to use ideas from continuous time dynamical systems and control and apply them to meta learning. In other words, to learn how other people learn and infer their learning policies. Okay. Okay. So let's see. So first, in order for me to do that, I have to define a score function, okay, that will encode the memory of each player. And of course, this zeta I0 is everything is biased towards the initial beliefs. So again, this is the score function, and UI here is the utility function of every player. Okay. So since we're controls people, every time I see something like that, I want to take the derivative, right? So if I take the derivative, then I have something that is like that. Okay, it's a system that is very well known. Okay, so but now I want the choice map, okay, to be derived by this framework here. Okay, where I want to make sure that everything is regularized. That's why I have this choice map. Okay. Okay. So what I want to do here is I want to see if an intelligent player in any game can take advantage of the opponent's learning mechanisms. I want to see if a smarter player can understand how the other players learn and adapt. Okay. And in order for me to do that, I want to learn the learning mechanism. So again, I want to learn what is the learning mechanisms of the other agents. Okay, so the first thing that will come to my mind is to employ mimicking dynamics, okay? And this will help me not only to reason about the game, but also to adapt, okay? So the first thing that I will do here is I will assume that I have known player utilities, okay? You will see I will relax this assumption later. Okay, so if I have known player utilities, the first what I want to do is I want to approximate only my cost function. Okay, my score function, sorry. And so in other words, I will use only one approximation structure. Okay, and the choice map will be given by this one, where W is the unknown weights that we will derive soon. Okay, so the intelligent player will measure the actions, okay, and will minimize this prediction error. And then after I use a classical gradient descent, I can find a way to tune this weight and eventually approximate my my score function. Okay, so and this is our little theorem here. So it says that the player I of high cognitive abilities, and given a network structure update loss, we can provide that everything is bounded, and given specific conditions, we can even provide asymptotically stable guarantees. Okay, so now we can extend this meta learning where we don't have any knowledge of the opponent utilities. Okay, remember before I knew the opponent utilities, and then I derived my score functions. But now here my choice maps, I'm sorry, but here I don't have any knowledge of the opponent utilities. Okay, so now instead of using only one approximating structure, what I will do is I will do two approximating structures and only one measurement. Okay, so first we will restrict our attention to Polymatrix games. Okay, so Polymatrix games, I'm sure all of you are familiar. Okay, we'll have a matrix game where one player picks the rows and the other player picks the columns, and then I can have multiple of them. Okay, so now instead of having only one approximating structure, I will have two of them, where I will also estimate my opponent's utilities. Okay, and how I can do that, I will use the very well-known backpropagation through time. Okay, so I will learn my choice map via this rule, okay, and the utility based on sigma modification of the gradient descent. Okay, so again, my choice map is learned by this tuning law, and then my utility is learned by this other tuning law, which is similar to sigma modification. Again, I don't require any pre-training, everything will happen in real time. Okay, and yeah, those backpropagation through time, so I propagate my derivative through time, and then you can see I have this change of integrators. Okay, so again, here I can still provide that the estimation errors are bounded, but of course here I cannot prove asymptotically stable guarantees, but just uniformly ultimately boundedness. Okay, so we have also extended this thing where, not in the Polymatrix games, but when we do pure optimal control, and then I want to manipulate my learning components. And so you can think that I want to do that for deception. Okay, so I want to learn my opponent's utilities. I want to deceive them, okay, to pick the wrong actions, because I'm learning what they're learning. And based on that, derive my policy eventually. Okay, so in optimal control, the intelligent player objective can be formulated like that. Okay, so here I have my utility function, and I have two constraints where my choice maps, they're bounded in the simplex, and then this constraint makes sure that eventually what is learned is what they want. Okay, so the intelligent player, as I said, 6 equilibrium points of the learning process that are optimal with respect to the higher level objective. That's why they're bounded inside their probability simplex. Okay, so what I want to do is I want to design these optimal trajectories to stay at required points. Okay, and I want to introduce optimal control methods to do this learning. Again, I want to learn how the other agents learn optimally. Okay, so the first thing that will come to my mind is to derive my performance. But again, my dynamics here are given by this dynamics here. Okay, so my x dot equals to u is just a single integrator that will make sure that everything lies inside the probability simplex. So and also for trajectory smoothness. Okay. So my q x comma z enforces convergence to drive behavior, and then r x comma u is how I penalize my choice map and my u. Okay. So of course we have everything that we prove that everything eventually remains in the probability simplex, and given specific cost and constraints. So the control that I want to derive will optimize this, what we call PreHamiltonian, which is similar to the Hamiltonian, but I will have my two costate variables that they will actually augment my dynamics back with my performance, such that I make an anchor state optimization, to an anchor state optimization. So this is exactly how you derive your U star, okay? And my augmented Hamiltonian doesn't require any extra constraints because everything is augmented. Okay, so the derived optimal control signal is given by this law, okay? Okay, so now we want to derive this feedback control. I want to obtain the optimal value function and then eventually solve the Hamilton-Jacobi-Bellman equation of the specific problem, okay? And yeah, so then this is just some simplifications on that. So eventually, if I solve this corresponding Hamilton-Jacobi-Bellman equation, so then I know how I can derive this feedback control problem to learn how the other ones are learning. Okay, So now let's actually see how everything works. So first, I will assume that I have a non-utility functions, and I will do that for the famous two-player Pennymatic game. Okay, so my first, the utilities are U1 and U2, okay, where since this is a zero-sum game, right? So I have that the U1 is given by that and U2 is that, and then the A and B, they have different signs, okay? So eventually you see that I have actually be able, for a non-utility function, I was able to identify properly all the components of my B matrix, okay? And then eventually I was able to learn how the other agent was learned. So you see this error eventually went to 0, okay? Yeah, so this is the intelligent player eventually learns the utility function and the opponent choice map. Oh, and then that was, and then to conclude, so what I have done is I formulate the cognitive hierarchy in linear quadratic games. I applied that to pressure evasion games of multiple UAVs and stochastic games later. And then I introduced a Metalearning framework in games and formulated a learning manipulation problem. Because of course, if I learn how the other agents are learning, then I can deceive them and make them learn what I want to learn. There's lots of things to do for future work. So we want to apply and investigate different models of bounded rationality. We want to explore more optimal control structures in learning scenarios. And then we want to actually see how meta-learning can manipulate attackers' beliefs and attackers' capabilities. And with that, I would like to thank my students, Aris, Philippos, and Nikos, for doing this work presented here. And of course, the funding agencies that without them, nothing will be possible. And I will be happy to answer any questions.
Thank you, Kyriakos, for the great talk. Any question from the audience? You can simply unmute yourself and ask a question.
Yeah, Kyriakos, yeah, thank you. Thank you very much. Now, there's one thing that can you go back to the definition of the levels?
Yes.
Of the players?
Let me see what slide was that. This one?
So when you say level 1, so level 2 responds to environment to level 1 or to level up to 1?
Okay, so if we do level K thinking, so the level 1 best responds to level 0. If we go to cognitive hierarchy, then for example, if we have a level 2 agent, then it will actually respond to a distribution of players that they're below here. So level 2
including 0 and 1.
Yeah, 0, 1, yes.
But you don't know how many players are level 0 and how many are level 1.
No. Yes, no, we don't know. And so we interact with them, and based on that, we compare their policies with our database policies, and then we actually say, okay, so this player is of level 1 with a probability 40%.
What kind of, and there is a notion of convergence in the sense that.
So for some specific actually cases, for we can provide convergence to Nash when your levels go to infinity. But for
right,
every
so that was I was wondering, right? So if there is a notion of convergence in K, convergence to something, right?
Yes, exactly, yeah. So we converge to something in below in every level, but we cannot quantify it in all cases how close to Nash it is.
Mm-hmm.
So sometimes, even if you take the K to infinity, you will never be able to converge to Nash. But again, this is most of the case not a bad thing, but sometimes, most of the times, it's a good thing.
First of all, I was wondering about convergence, right? Because and then conversion to
Yes. So all these the polyiteration and validation algorithms, we prove through contraction mapping that they actually converge. And then for some specific cases, we can even provide convergence to a Nash if we take the case to infinity.
Mm-hmm. But this also builds on assumption on what is the distribution of agents. What if you get that wrong?
Yes, exactly. So if you get that wrong, yeah, so it won't be the Nash. But or it
will not be the Nash, but yes. But it will still converge to something.
It will still converge because they're bounded. It's nothing is open loop here. Everything's closed loop, so it will still be bound by the trajectories of the systems.
Mm-hmm. And what is the advantage of the level K thinking? Is it computational, kind of like the way to compute it?
Computational, and also if you have human in the loop components in the several physical systems, so most of the times they don't play Nash, but they're either random or they're below Nash. So Cameron and Ho they provided that humans, they act up to level 3, and they had human experiments with centipedes, I think, and they have proofs of that. So level 3, that they're most humans, and level infinity, that in some cases it's Nash, it's very far away, it requires lots of computational efforts to compute those things.
What if a player has, so you mentioned the fact where players have different utilities, right?
Yes.
Or what if some players are just not rational?
Oh yeah, exactly. So this actually, the bounded rationality actually takes into account that some players, they're not even rational.
Right. So it's a notion, right? But
yes.
The bounded rationality is a notion, but is that captured by this level K thinking?
Yep.
Okay. Because of the distribution that you
exactly assume. Yeah, exactly. Because of the distribution of the Poisson distribution, that we assume that everybody's below us, and then we train our policies based on that.
Mm-hmm. Okay, I need to wrap my head around this a little bit. Okay, thank you, guys. I want to leave some time for others as well.
You're welcome. Thank you, Emilio.
I have a question.
Yes.
Yeah, Edzat, go first. I'll do the judge that decides who go first.
Thank you for the talk. I have a related question to Emilio's, also about this level K thinking. So if I understood, please clarify if I understood this correctly. This is essentially a way to solve the game a priori, right? So every one of these levels solves the game a priori, and then just plays the policy they solved.
What do you mean a priori?
So level 0 agents so every one of those K levels solves the game a priori before playing it. By doing one, like if you're a level 0, you will do 0 iterations. If you're a level K, you would do K iterations, and then go and play, and then every level goes and plays their policy, let's say, forever. Is that correct?
So no, let me clarify. So again, don't confuse the K with iterations, and so that's one thing. And then for the first part that I present is for the L2R games and the dynamic games. Nothing is pre-computed, so everything happens in real time. So the levels are learned through learning in real time. But in order for me to find and map to what levels of intelligence I have a database of policies that I will compare those to. but everything happens in real time and online.
But these database of policies comes from pre-computed policies.
Yes, I mean the level of the policies, yes, comes from the computed, but the policies are computed. The policies are computed in real time. But the levels, the mapping of levels, I have to compare it to something I already have.
So I guess my question relates to like, how does this relate to repeated play? So there's all this literature on learning through repeated play. And even if you just best respond to what you've seen before, it's not that you are best responding to the best response and the best response of the best response. So to me, that's like a level 1. You just best respond to what you've seen before. There's literature that this would converge to a Nash equilibrium.
Yes. Okay.
So how does this fit with that?
Okay.
So if basically if you're doing an iterative best response, where the best response is just a level 1 best response,
okay,
you would in many games converge to a Nash equilibrium, like potential games and so on. So
okay.
How is
so
that
let's say
to...
Yes, so let's say so you actually you put in level 1. So level 1 will actually optimally respond to level 0 always. So level 0 is a random player.
Okay.
So this will never converge to a Nash.
So the level 1 optimally does not optimally respond to whatever they're seeing necessarily. They are optimally responding to an assumed level 0.
Yes. Okay. Again, so I'm let's say the player, and I will assume that I will interact with different players. Okay. So let's say I'm level 1. So I will best respond to a level 0. Then if I go to level 2, I will optimally respond to a level 1, and so on and so forth. But in order for us to converge to a Nash equilibrium, this best responding of one level by assuming everybody's below, it doesn't suffice to prove convergence to a Nash. Actually, it will do it only in specific cases, and even that, it is very tricky to find the cases. But this is different from repeated games, because repeated games already know the existence of the games, and they already they already optimize the worst case or the best case of the other players. So here you can think that they don't share the decision-making mechanism, and they have different computational capabilities. If you go back to repeated games, so they share the same decision-making mechanism, and they have the same computing capabilities.
I guess what's a bit not clear to me is if we take level 1, they are optimally responding to level 0 agents, right? But what if the agents that are in real life are not actually level 0 agents?
Oh yeah, that's why we train all this. We learn all these policies in real time, and eventually we compare those with the database.
Okay.
So if you compare those with the database, then you find, okay, let's say I'm level 5, and then I think that agent 1 is level 1 with probability 60%.
Yes. So yeah. Okay.
Thank you. Thank you, Azad.
Thank you.
That next question was from Emrah.
Hi.
Hey, Emrah, how are you?
Good, how are you? Thank you for the nice talk.
Good.
So I just had a quick question. So if these attackers know that the defender is measuring their levels, can they fake a lower level at the learning period? For example, I am level 10, but I am acting like level 1 to trick the defender so that, you know, can it be beneficial, or is it something not practical? What do you think?
Actually, that's a very, very interesting question. So definitely the first parts, they cannot handle that, but the meta-learning part, where actually I'm learning how the agent is learning, and I don't map it to specific levels. So then I think we can tackle it, but we haven't really worked on that, but that's very interesting. So you mean that I want to deceive, so deception, right? You mean I want to deceive my opponent to believe I'm level 1, but I'm actually level 3.
Yes, exactly.
Yeah. So I think eventually our meta-learning, which was on the second part of the talk, can eventually handle these situations, but we haven't really tested it with different levels, because I can learn how the other agents are learning and deceive them, because I can adapt my strategies, and then if I adapt my strategies, they're also adapting the strategies, and so on and so forth.
I see. Thank you.
You're welcome, Emra.
Thank you for the question. Any other question?
Yeah, I had a question. So,
Go ahead.
like, since I'm a controls guy, I always look for connection between the control cost and the noise. So what is the connection that you've done to that?
The noise. So
Yeah,
you can
noise.
think that level 0 agent can be any random thing. It can be a noise. It can be anything that is of random. So anything random can be a Gaussian noise, anything you can imagine.
Okay, so the variance of noise scales with the control cost then, right?
Yeah.
So that means that the HJBs can always be linearized. So that is the assumption that you imposed, that if the variance of noise is scaling along with the control cost, the HJB can always be linearized. Because the control authority will take care, control cost will be higher when there's higher variance.
Okay.
So your HJB will always be, can be linearized always, right?
I don't understand. So can you explain more?
No, I mean, since the variance of noise, it scales with the control cost. It means basically that when the noise is high, you're giving control more authority to take over.
Okay. But again, remember that everything has to do with a performance. Okay. So, and then that the controller is the minimizer. So if you do level 0, so let's say that your disturbance is of any noise you want, but my control input in the for level 0 will assume that there is no disturbance there, there's no noise. So.
Okay. Yeah.
Yeah.
Thank you.
You're welcome.
Thank you for the question. Any final question for Kyriakos? Does it seem so? I think you gave your email in case people want to reach out.
Oh yeah. So any questions, any papers you want to request, just shoot me an email. I will actually share anything you want, and I will answer more questions.
Thank you very much, Kyriakos, for the talk.
You're welcome, Joel. Thank you very
time.
much for the invitation. Emilio, always good to see you. And thank you for the invitation again. And yeah, and I will be happy to see your emails from any of you asking questions. I know I try to incorporate many things, but hopefully you get an idea about how we can get bound rationality, different things in several things of controlling games, and make some interesting conclusions.
Yep, definitely. Thank you very much, and good luck for the next steps.
Thank you.
Bye-bye.
Bye.
See you all next week. Bye.
Yep.